Good evening, we're Group 12. We're going to present a reading about attention to you. Real-time fMRI links subjective experience with brain activity during focused attention. We will go through a summary, including background, method, results, discussion, limitation, and conclusion of the study before our evaluation and critique, including study design and future directions. Recent advancements in brain imaging have improved the measure of neural processes, but the relation between brain activity and subjective experience remains poorly characterized. This study links objective brain activities imaging and participants' subjective experience using the real-time functional MRI, collecting neurofeedback from the posterior cingulate cortex (PSYC) to provide real-time feedback during a focused attention task. The default mode network (DMN) is an interconnected group of brain structures that are hypothesized to be a part of functional system. It includes the medial prefrontal cortex, posterior cingulate cortex (PCC), and inferior parietal lobule. Studies shows that DMN was related to mind wandering. When people are at rest or doing nothing, the DMN activities increase. In contrast, DMN activities decrease when people are doing cognitive tasks and having attention awareness of presence, for example, during meditation. Posterior cingulate cortex (PCC) in DMN is the key part of research in this study. It locates at the back of the anterior cingulate cortex and is active when subject is mind wandering. Neurofeedback from PCC in DMN is collected using real-time fMRI. PCC was used for neurofeedback because PCC deactivation was the most robust finding in experienced meditators in prior studies. Real-time fMRI provides feedback of brain activity during an ongoing task. There are some advantages of using real-time fMRI. In this study, it provides real-time feedback from brain activities of subjects during an ongoing task, and it allows tighter monitoring between real-time reports of experience and corresponding measures of brain activities. In addition, real-time fMRI provides high spatial resolution with improved temporal resolution and is used to provide neurofeedback from the PCC to participants inside the MRI. As mentioned previously, this study aims to test the feasibility of using real-time fMRI to link ongoing subjective experience with an objective measure of brain activity in real time during focused attention. There are two experimental groups, adventurous group meditators and control group non-meditators. Experiments 1A, 1B, and Experiment 2 are conducted in this study. This experience contrasts the performance of meditators and non-meditators in staying focused. In Experiment 1A, 22 experienced meditators and 22 non-meditators were shown real-time brain activities in PCC or control region PPC during a focused attention task. They were shown graphs with red upward signals, meaning activated in PCC for mind wandering, or blue downward signals, which means they stay focused. Then they were asked how well the feedback graph corresponds with the subjective experience of focused attention or mind wandering. Experiment 1B is the sampling of some participants from Experiment 1A. 9 meditators and 11 non-meditators were asked to make the graph go blue. It means to ask the participants to stay focused, to voluntarily deactivate PCC to make the graph blue. Experiment 2 aims to replicate Experiment 1 with their potential confounds of experiential anchors for the graph focused attention and mind wandering provided in the earlier experiment. In this experiment, a separate group of meditators took part in a novel stepwise real-time fMRI blinded discovery protocol in which they were instructed to use their subjective experience during the task to discover the relationship between their experience and the feedback graph. The subjects are instructed to decrease the feedback graph volitionally. Here comes the result. In Experiment 1A, the group of meditators and the group of non-meditators both reported significant correspondence between the feedback graph and their subjective experience of focused attention and mind wandering. And the mean correspondence rating did not differ between these two groups. The correspondence rating was higher for runs with feedback from the PCC than other parts of the brain. In Experiment 1B, when instructed to volitionally decrease the feedback graph, meditators were able to significantly deactivate PCC, which was not the case for non-meditators. This can be seen in the graph. The bars represent change in PCC. For meditators, there's no significant correlation between meditation hours and signal change in PCC. All participants reported linking between their subjective experience of focused attention and decreases in the feedback graph, which represents PCC activity. As we can see in experiment 1b, meditators show significant volitional decreases of the feedback graph. Here comes the discussion on limitation of the study. The study shows that it is feasible to closely monitor real-time objective measure of brain activities in PCC and momentary subjective experience of participants in a focused attention task. Experienced meditators show significant deactivation of PCC during volitional degrees of the feedback graph in blinded discovery protocol. However, telling participants that blue downward signals stand for focused attention and red upward arrows for mind wandering would bias participants' self-reports. Meditators perform better than non-meditators in staying focused with their expertise at focused attention and monitoring of experience. This shows volitional degrees brain activities in the PCC area in experiments 1b and 2. A limitation here is that focused attention was decontextualized in the real-time fMRI. Traditional meditation practices usually involve contextual components, such as background beliefs. The study cannot rule out the possibility that larger meaning components of the practice or memory of other practice contexts may be active even during the decontextualized focused attention task. The study discovers that activity in PCC is related to focused attention and mind wandering in real time. The findings support the use of real-time fMRI neurofeedback in cognitive neuroscience research to assess the linking between real-time feedback from brain activity and concurrent self-reports of mental states. Moreover, they add conversion validity and improved temporal resolution to prior studies. The potential problem of reverse inference was tackled by having participants to report their direct experience as it corresponds with feedback. However, this does not imply that single brain regions such as PCC can wholly account for complex cognitive processes such as focused attention. To overcome this limitation, the writer suggested using real-time feedback from multiple hubs or functional connectivity between hubs. In conclusion, real-time fMRI provides a novel methodology tightly linking the dynamics of subjective experience and changes in ongoing brain activity. This technique can be applied in future studies like neurophenomenological investigation and testing the robustness of cognitive strategies and tasks in real time. Besides, experienced meditators are found to be a population of choices for future studies with their higher level of introspective awareness and ability to detect subtle changes in subjective experience in real time. For critique section, here are some recent literature research to begin with. Overall, we think this is a good scientific research. The diagram highlights an attempt to close the literature gap by connecting an ongoing subjective experience, which is focused attention, to objective brain activity measurement through real-time fMRI. A listed stimuli was selected to facilitate attention focus among study subjects for generating brain transduction activity systematically. In neuroscience, DNS is a common brain study area under the study focus. PCC was selected to act as a proper baseline, and PPC is used as a control region. Besides, gray matter was named as region of interest that is closely correlated to meditation experience. Real-time fMRI is a proper brain imaging method. However, subjects need to stay still to finish the tasks assigned under loud noises. This situation can affect the overall quality of focused attention state during the testing process. For experiments 1A and 1B, the Theravada tradition was the dominated traditional stream. A higher numbers of the traditional meditation streams were included in experiment 2 to provide a comprehensive evaluation. It can lead to some inconsistency while they were entering the focused attention stage because of the different beliefs, cultures, and expectations. For experiments 1A, sample size and sampling criteria are totally the same for both groups. For experiments 1B and 2, the sample size of target study group was relatively small, with fewer than 20 subjects in total. And in experiment 2, one subject features with ambidextrous that forms a different measurement baseline due to his or her variation of brain structure and brain activities. These flowcharts outline the well-tailored operation steps to execute the study smoothly. Each phase was assigned to different tasks for gathering rich data in response to selected study focus. This summary outlines the advantages in blue and disadvantages for all three experiments about their operational standards and procedures. Real-time fMRI lifetime delays can be seen as a technical issue that created moment-to-moment brain measurement barriers. Besides, in experiment 2, one subject was late for the test and missed step 4. Researchers adjusted their statistical methodology to act as a quick fix, but to some extent this can still affect the validity of relevant findings. Regarding statistical methodology, this table explains relevant advantages in yellow as well as disadvantages for all three experiments. Overall, they did a good job in terms of proper monitoring and cross-checking. This study also used a range of statistical methods for each round of experiments by SPSS to produce relevant findings effectively. For experiment 1B, anchors were added to establish a different result. This can develop personal bias. There are several ways to improve these studies, such as adding real-time EEG, enhancing study sample size to 50+, selecting other baselines to execute a detailed comparison, involving other brain areas, and operating these experiments in natural setting. Here are some further study directions in the future. For example, lengthening overall study time frame, expanding the variety of sample profiles such as age, race, occupation, along with the consideration of cross-cultural differences. Here is our reference list. This is the end of our presentation. Thank you for listening.